Steel wheels meeting steel rails create one of the most efficient transport systems ever devised, yet it is efficiency born not of power, but of restraint. The contact between a railway wheel and the rail beneath it is remarkably small, no larger than a coin. On worn wheels, it can be smaller still. That tiny interface carries tens of tons and determines whether an entire train moves or remains immobile. The key lies in rolling resistance, not friction in the everyday sense. Sliding friction, the force felt when dragging a heavy object across the floor, resists motion continuously. Rolling resistance behaves differently. Once a wheel is turning, the energy lost to deformation and surface roughness is minimal. Steel on steel, when properly machined and maintained, deforms very little. The result is a coefficient of rolling resistance far lower than that of rubber tires on asphalt. A road vehicle must constantly fight friction simply to keep moving. A train, once in motion, largely coasts. This physical reality explains why railways became the backbone of industrial economies. A single locomotive can haul thousands of tons not because it is extraordinarily powerful, but because the system wastes so little energy. The smoothness of the rail, the hardness of the wheel, and the narrowness of the contact patch combine to reduce resistance to a level road transport cannot approach. What appears to be brute strength is in fact mechanical economy. Yet this efficiency carries an overlooked consequence. Because so little force is required to keep a train moving, the labor and risk concentrate at moments of transition. Starting, stopping, coupling, uncoupling. These are the points where human judgment matters most and where workers historically paid the price for institutional pressure to move more, faster, and cheaper. The physics that allow enormous loads to glide almost effortlessly also leave little margin for error when conditions change. Steel on steel does not forgive complacency. Rain, leaf residue, or poor maintenance can turn low resistance into lost control. The system remains neutral, indifferent to outcomes. It is the people working within it who absorb the consequences when efficiency is prioritized over safety. The quiet glide of a freight train, passing without strain, masks a balance of forces that has shaped industrial history and the lives bound to it, often without recognition or reward. Once rolling resistance has been minimized, the remaining challenge is grip. A locomotive cannot pull anything at all unless its wheels maintain adhesion with the rail. Unlike road vehicles, trains do not rely on soft tires deforming against the surface. Their grip comes almost entirely from weight. A modern freight locomotive weighs in the region of 120 to 130 tons, and nearly all of that mass is deliberately concentrated over a small number of driven axles. Typically, 12 steel wheels carry the entire load. Each wheel presses tens of thousands of pounds onto a contact patch no larger than a coin. This pressure creates adhesion, the resisting force that prevents the wheel from slipping as torque is applied. Engineers describe this relationship through the coefficient of friction between steel wheel and steel rail, usually around 0.3 under clean, dry conditions. The available pulling force, known as tractive effort, is simply the weight on the driving wheels multiplied by that coefficient. This calculation imposes hard limits. Apply more torque than adhesion allows and the wheels spin, polishing the rail and making the problem worse. Early railway operations were shaped by this constraint, with crews disciplined or dismissed when will slip damaged equipment or delayed traffic. The system offered little tolerance for error, and responsibility often fell on individuals rather than institutions. To manage these limits, locomotives were fitted with sanders, small hoppers that deposit sand directly ahead of the driven wheels. In rain, frost, or autumn leaf fall, a thin layer of crushed vegetation can reduce adhesion dramatically. A brief burst of sand increases friction enough to restore control. It is a simple intervention, but one that has prevented countless stalls and collisions, often without acknowledgement. In recent decades, traction technology has shifted again. Older direct current motors delivered power unevenly, making precise control difficult at low speeds. Modern alternating current traction motors, governed by computers, constantly monitor wheel speed and adjust torque in milliseconds. The result is more usable tractive effort, fewer wheel slips, and less reliance on human reaction under pressure. Yet the underlying principle remains unchanged. A locomotive does not overcome physics, it works within it. Its weight provides grip, its systems manage restraint, and the burden of making it all function safely has historically rested on crews operating within tight margins, where failure was personal and consequences long-lasting. When a freight train stands still, the greatest obstacle is not distance or speed, but inertia. Every wheel on every wagon is held in place by static friction, the same force that makes a heavy object resist movement until it suddenly breaks free. For a long train, this resistance accumulates into an enormous barrier. On level track, each ton of stationary freight may require several pounds of force just to begin rolling. Multiply that across thousands of tons and the numbers quickly exceed what a single locomotive can overcome in one attempt. If all that resistance were applied at once, the result would be immediate wheel slip, damaged rails, and no movement at all. The solution is not greater power, but sequencing. Hidden behind every coupler is a component rarely noticed outside the railway, the draft gear. These devices sit within the coupler assembly and allow controlled movement, several inches of travel as the coupler compresses and extends. To an observer, this movement is invisible. To the physics of starting a train, it is decisive. When the locomotive applies power, it does not pull the entire train simultaneously. It pulls the first wagon. The draft gear compresses, absorbing force while that single car overcomes static friction and begins to roll. Only then does the coupler to the second wagon engage, allowing the next car to move. The process repeats, one vehicle at a time, as motion travels down the length of the train. Railway workers refer to this as slack action, and its sound is familiar to anyone who has stood near a departing freight, a measured sequence of metallic knocks as each coupler takes the load in turn. On a long consist, the effect is striking. The locomotive may already be moving steadily while the last wagons remain stationary, waiting for the wave of motion to reach them. Without draft gears, the locomotive would be forced to fight the static friction of the entire train at once. No realistic increase in engine power or weight could solve that problem. Brute force would simply polish wheels and rails into useless smoothness. This system did not emerge by accident. It reflects generations of operational experience, hard limits encountered in yards, on gradients, and under time pressure. Draft gears quietly protect equipment, schedules, and crews, yet they rarely feature in public accounts of railway efficiency. Their absence would make modern freight operations impossible, turning the physics of starting a train into an unsolvable problem and shifting the consequences, once again, onto the people at the controls. If you found this story moving and want to learn more about forgotten moments in history and the people behind them, make sure to like this video, subscribe for more in-depth documentaries, and hit the notification bell so you never miss a story like this.